بسم الله الرحمن الرحيم. بنرحب فيكم في المحاضرة رقم 9 من مواضيع خاصة في الاتصالات والإلكترونيات. احنا بنتكلم عن طبعا موضوعنا في الاوبتمايزيشن، وراح نتكلم اليوم برضه نكمل في بعض الاتerative algorithms for optimization. اليوم راح نتكلم عن موضوع جديد أو ميثود جديدة، خلينا نحكي، اللي هي نيوتنز ميثود. So we will continue in lecture 9 about iterative algorithms for optimization. وراح نتكلم اليوم عن نيوتنز ميثود. اوكي، خلينا نحط بعض النقاط المهمة. The derivation of the steepest descent algorithm was based on the first order Taylor first order approximation. Let's say approximation of Taylor series expansion, while Newton's method is based on the second order Taylor series. Expansion. Okay. Another way we can say that we have fx of k plus 1 is equal to f of x at k plus delta x at k. And this is approximately equals to f of x at k. We expand we make the Taylor series expansion around the older guess, which is f of x at k plus g. Let me just put it down here. This is equal to f of x at k plus g of k transpose. This is the gradient times delta x at k, delta of x at k, plus the second order term, which is 1/2 delta x at k transpose ak delta x at k. Okay, and you have other terms. So you have the approximation. We just ignored or neglect the higher order terms more than the second order. Remember that this a is actually ak is equal to the Hessian of f of x at k, the Hessian matrix. Okay. To do the Newton's method, we will do the following. We would like to take the derivative of f of x of k plus 1 with respect to delta x at k. So we would like to see what should be delta x of k. Differentiate this one with respect to delta k so that you know what is the best delta k that will minimize this function. Before we go to the derivative of this function here, let me just put some useful properties of the gradient. If you do the gradient for an inner product between h and x, and h is a constant vector, this is also equals to the gradient of x transpose h, and this is equals to the h vector, where h is a constant vector. Okay? So this is in mathematics, the gradient of the inner product where h is a constant actually, constant vector. X is our variable, the gradient of x, but we have an inner product, h transpose x. This is equals to h. And the gradient of x transpose h is also equals to h. Okay, one more property that is also important to us at this moment, which is the multiplication of the second order. So the gradient of x transpose q is a matrix. X is equal to qx plus q transpose x. If q matrix, if the matrix q, let's put it this way, if the matrix q is symmetric, the matrix Q is symmetric, then, which means that Q is equal to Q transpose, then the gradient of X transpose QX is equal to 2QX. Taking those two useful properties of the gradient, this one and this one, into consideration to make the derivative of f of x of k plus 1, which is equal to this term plus this term plus this term, and take those two identities into consideration, we can say that the gradient of f of x of k plus 1 is equal to the gradient of this one. This is a constant, so its gradient is equal to 0. And you are taking the gradient with respect to delta x, so the first one will be g of k without transpose, taking into consideration this useful property. Gk is the constant, this one is the variable, so it's as if you are having h transpose is, so gk is your h, x is your delta x, so the derivative is g plus. Now you have this one, it's the same form as this one, ak, which is the Hessian, this one is symmetric, so it's 2qx So this one will be 2 AK delta X, but you have 1/2 here, you have 2 here, so you end up with A sub K delta X sub K, and you equate this to be equal to 0. So solving for delta X sub K, this equals to minus A sub K inverse G sub K. So Newton's method is defined as x at k plus 1 is equal to x at k minus A sub k inverse G sub k. So this is my delta k, delta x of k. So this is the new one based on the second order information, which is the Hessian. And this is the Newton's method. Okay? I'm going to take the following example and solve it using the Newton's method. So example 1, let f of x equals to x1 squared plus 25 x2 squared. So this is a second order function. It's elliptic functions, or the level curves or the contours are elliptic functions. Okay, we will use the Newton's method to find the minimum of this function. Use Newton's method to find the minimum. Okay. So first of all, I'm going to find the gradient of f of x, which is equal to partial f of x partial x1 partial f of x partial x2. This is equals to 2x1, and this here is 50 x2. And the Hessian of f of x is equal to this one is 2, 0, 0, and 50. The second derivative of this one is with respect to x1 is 2, with respect to x2 0, this one with respect to x1 0, with respect to x2 is equal to 50. Okay, if we start from some initial guess, say x0 equals to 0.5 and 0.5. So let's see what will happen with the first step. Because the Hessian here is constant value, so it will not change with changing the values. I mean, if x1 changes from 0.5 and 0.5, the Hessian is always constant. This is always constant matrix. And so AK is always equal to 2, 0, 0, 50. And what will be AK inverse in this case? It's very simple because you have only diagonal elements. So this one is 1/2, 0, 0, and 1/50. This is the inverse of this matrix because this is only diagonal elements. So the inverse is the reciprocal of each element in the diagonal elements. Okay. So the first step of Newton's method would be x1 equals to 0.5, which is x at 0, minus A inverse, which is 1/2, 0, 0, 1/50, times the gradient at x0, so 0.5 times 2, it's 1, and 0.5 times 50, it's 25. So this is equals to 0.5 minus 1/2, so this is 0.5, 25/50, this is also 0.5, and you will get a 0 and a 0. And actually, you get, this is the minimum. Or, sorry, not the minimum, it's x at which we have a minimum. Okay? If you apply 0 and 0, so you have f of 0 and 0 is equal to 0 squared plus 25 times 0 squared is equals to 0. What we have noticed here is that if you have a quadratic function, as we have in example 1, you would reach the minimum in one step. So this method, or Newton's method, this method will always find the minimum of a quadratic function in one step. This is because Newton's method is designed to approximate a function as quadratic, and then locate the stationary point the stationary point of the quadratic approximation. Okay? So when we took this example, our function was quadratic function. It was x1 squared plus 25x2 squared. So this is a quadratic function. This is why in only one step, at any initial condition, you can reach x1 to be your final answer to be the minimum by one step. So if the original function is indeed quadratic, it will be minimized in one step. Okay? Okay, what if the function is not quadratic? If the function if the function f of x is not quadratic, then Newton's method will not generally converge in one step. In fact, we cannot be sure that it will converge at all, since this will depend on the function f of x and its the initial guess x0. So choosing x0, maybe you will go to somewhere else if you choose another x0. We'll see this through the following example. I'm going to take a function Okay. So the function itself and the initial guess are two critical parameters to be considered when talking about the Newton's method. We'll see this through the following example. So if we consider f of x to be equal to x2 minus x1 to the power 4 plus 8 x1 x2 minus x1 plus x2 plus 3. This is a fourth order function, okay? And by solving this function, we can find that this function has three stationary points. The first one, x with a superscript, means that this is the first of those stationary points, is equal to minus 0.42 and 0.42. The second stationary point, x2, is equal to minus 0.13 plus 0.13. And the third stationary point, x3, is equal to 0.55 and minus 0.55. So you have three stationary points for this function. The first point x1 is a strong local minimum. The second one the second point, x2, is a saddle point. And the third point, x3, is a strong global minimum. Okay, so you have 3 points. Now, if the reason why I'm taking this example is that just to show you that depending on choosing our initial guess, you can go to point number 1 or 2 or 3 based on the choosing of your initial guess. Definitely what we are looking for is to go to the strong global minimum, but sometimes you will go to this one or you go to this one based on choosing of your initial guess. So if we apply Newton's method to this problem, starting from the initial guess, x0 equals to 1.5 and 0 transpose, the algorithm will converge to the global minimum. Okay? If the initial guess x0 was equal to minus 1.5 and 0 transpose, the algorithm will converge to the local minimum. And if the initial guess And if the initial guess x0 was equal to 0.75 and 0.75 transpose, the algorithm will converge to the saddle point. So this is a drawback actually for Newton's method. The first drawback is it's dependent on the function itself and the initial guess. So sometimes if you choose the initial, you are lucky and you get the initial guess right, you go to the global minimum, but sometimes you will not. And the other drawback of the Newton's method is the computation of the Hessian matrix. The Hessian matrix is the second order derivative, and every time you have to calculate the Hessian matrix, especially if you have a higher order, nth order parameters. You know, with 2 parameters, it's somehow an easy job to do, but if you have like 100 parameters, then you have 100 times 100, so you have 10,000 derivatives to be calculated in the Hessian matrix. Definitely, this is not actually the number. It's probably half of that because of the symmetry of the Hessian matrix, but still it's a tedious or difficult job to do, to calculate the second derivatives of or the elements of the Hessian matrix, which are the second derivatives of the functions inside, the parameters inside. Okay, with this we end up with the Newton's method, and we are going to look forward to modifications of the Newton's method or new ways to overcome the difficulties that we faced in the Newton's method. Thank you very much, and looking forward to see you in next lecture. Thank you.